So now we're actually going to graph the sine and the cosine function. So first, recall from your previous pre-calc course that you can deal with transformations of functions in this abbreviated fashion. If you can factor things nicely and you can set the function up, this parent function f of x, in this way, then the coefficient of f here does vertical transformation stuff. That is, it's going to do reflections across the x-axis and vertical stretches or compressions. B, which would really be the coefficient of x, so be careful you do have to factor that out, is going to end up being horizontal reflections and horizontal stretches and compressions. C is left-right shift. D is up-down shift. So a function is periodic if the range repeats over defined intervals of the domain. So this is a slightly different definition than what we used previously, but it is equivalent. Now, the shortest repeating portion of the graph, you could call that a cycle. Sometimes you may see cycle being used. And the length of the cycle is called the period. So really, period here is strictly a length. Now, we're also going to need to know what this amplitude is. And the amplitude of a periodic function is going to end up being half of the difference between the max and the min. So what you do is if you want to find the amplitude A, you just take max minus the min, and then you divide it by 2. Whatever max minus min divided by 2 is, that's the amplitude. Let's just graph the sine function the same way we'd graph any of our other functions. That is, we can use a table of values, pick some x values, plug them in, evaluate sine at those values, and then plot the ordered pairs. So I have picked some x values. So let's plug 0 into the sine function. Well, what is sine of 0? If you use your unit circle to find the answer, well, the sine of 0 is 0. So then we get the ordered pair, 0, 0. I'm just going to plot these ordered pairs as we go. Then let's plug in pi 6. What is sine of pi 6? Well, sine of pi 6 is a half. So then we get the ordered pair, pi 6 a half. Pi 6 is about right here. So pi 6 a half would be about right there. Then plug in pi halves into sine. Sine of pi halves is 1. Ordered pair is pi halves 1. Then we have sine of 5 pi 6. Sine of 5 pi 6 is a half. So that gives us this ordered pair, and that occurs about right here. Then we plug in pi. Sine of pi is 0. The ordered pair, pi 0. Sine of 7 pi 6 is negative a half. That occurs about right here. Ordered pair, 7 pi 6, negative a half. Plug in 3 pi halves. Sine of 3 pi halves is going to give us negative 1. Ordered pair. Sine of 11 pi 6 is negative a half, so that's going to be about right here. And then sine of 2 pi is, of course, 0, so that's there. And that's our ordered pair. Now, I'm only actually graphing this function for one set between 0 and 2 pi. Now, the reason I've done this is because we know that sine is periodic, and it has a period of 2 pi, and so from 0 to 2 pi, I should get one full cycle graphed here. And I claim that's exactly what we've done. We now have a graph of the sine function for between 0 and 2 pi. Now the truth is this function goes on forever in both directions, and so if you were to copy this image we have and paste it where we attach this point to this point, and then this point to this point, and then do it forever in both directions, you would get the graph of sine. And so here is a nice computer-generated version of the sine function, so we can look at it and we can talk about its properties. Some of these, once again, are just repeats of information. But what's the domain? The domain is all real numbers. Any value you want to plug into the sine function, you can. What's our range? Well, now it's easy to see that the range goes from negative 1 to positive 1. So there's our range. Notice that this function is symmetric to the origin, and therefore it's odd. So that's our definition. But just as a reminder, symmetric to the origin means that if you were to flip the image, rotate the image 180 degrees. Another way to do this is to turn around or turn upside down on your head and look at the image, and notice that if you look at it upside down, it's the exact same thing as it was right side up. and so that shows us that it's symmetric to the origin. And so our rotation to the origin has to be this direction, 180 degrees. That's our 180 degree rotation. Also, period is 2 pi, so notice that if you check out the distance between 0 to 2 pi, that's one full cycle. And then notice that from here to here is one full cycle. So the distance of 2 pi gives us a full cycle. Now notice there's other ways to cut it up. You could have done a full cycle between here and here. It's just a matter of preference, but we're going to take our full cycle to be between 0 and 2 pi. And so just some choices to show our period. Then the x-intercepts, where do they occur? Specifically, notice they occur here, 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 and here, and forever in both directions. Where is that? Specifically, that's at every integer multiple of pi. And so integer multiple of pi, 0 times pi is 0, 1 times pi is pi, 2 times pi is 2 pi, negative times pi is negative pi, so on and so forth. Our y-intercept is very specifically at the origin 0, 0. And notice that our maximum across the board is always going to be 1, unless we do some transformation, and our minimums occur at negative 1. So maximums and minimums occur here. And so if we want to label where those maximums occur and where the minimums occur, notice that the maximums occur at pi halves intervals. Not quite pi halves, but pi halves plus 2 pi. So every cycle repetition or every period of pi halves. So pi halves plus 2 pi n is where our maximums occur. And then at intervals of 3 pi halves plus 2 pi n, that's where our minimums occur. Then we can find our amplitude. Remember that the amplitude is the max minus the min. That is 1 minus minus 1 divided by 2. 1 minus minus 1 is positive 2 divided by 2 is 1. And so that's where our amplitude comes from. Which really, if you're looking at the image, the amplitude is there. Okay? Half the max minus the min is the amplitude, or how high is it from the 0 or the x-intercept to a peak or a trough. So then, let's talk about the graph of cosine. Well, we're just going to limit ourselves in graphing between 0 and 2 pi again. I've changed up the values that I'm plugging in for a slight reason, so be aware that we're not using pi sixths here, we're using pi thirds. But what is cosine of 0? Cosine of 0 is 1, and so that's that ordered pair we get. Then cosine of pi thirds is going to be a half. Pi thirds, 1/2 shows up about right here. Then cosine of pi halves is 0, so 0. Then cosine of 2 pi thirds is negative a half, that's about right here. Cosine of pi gives us negative 1, so that's here. Cosine of 4 pi thirds is negative a half, so that's right here. Cosine of 3 pi halves is 0. Cosine of 5 pi thirds is a half. Cosine of 2 pi is 1. And so then I claim we have one full period or one full cycle of our cosine function, so let's connect the dots. And so I claim that that's one full cycle. Notice that essentially if I cut and pasted or copy and pasted this on the tail end of each side, I would get the same type function that I had before. And so let's look at this all together. There it is. There's our cosine function. It goes forever in both directions. So then let's run through our basics again. The domain is all real numbers. The range again is between negative 1 and 1. This one is actually symmetric to the y-axis, thus even, so now it's easier to see that this is an even function. So that is, if you were to fold your image on the y-axis, notice that it would mirror each other or match up. If the period is again 2 pi. Now, we've cut the one we did a moment ago. That was our 2 pi interval, and then 2 pi to the left, 2 pi to the right. If you would rather think of the 2 pi in the same way we did our sine, you could put our 2 pi interval to go from here to here. That would also be one complete interval. You could measure that distance. Now, maybe it's worth mentioning that if you notice, this section sure does look an awful lot like sine. And so this will come up again, but we'll deal with that later. Then our x-intercepts are going to occur where? Well, they're going to occur at pi halves plus pi intervals. The y-intercept is specifically 0, 1. The maximums are going to occur at intervals of 2 pi, and so they're going to be at 0, 2 pi, and any integer multiple of 2 pi. Our minimums occur at pi and coterminal angles of pi. And then, of course, our amplitude is again 1. To put those transformations directly in the format that we're going to use them for our trig functions, here they are. So if we have sine or cosine, and I'm just going to leave this information for sine and cosine, it will relate to secant, cosecant, tangent, and cotangent, but not exactly the same way. So some of this information will change slightly when we get to those trig functions. So in this format, once again, b is factored out of x plus or minus anything else that's inside the trig function. But b would be a coefficient of x if it occurs. So, specifically, coefficients of sine or cosine, that's going to be our amplitude. Just ignore the sign on them, and that'll be amplitude. If a is negative, then that's going to make us have a horizontal reflection, or reflection across the x-axis. So you're really going to turn your functions upside down. Now the period is a little tricky, because specifically we know that currently with unchanged sine and cosine, that is nothing but cosine of x or sine of x, our period is 2 pi. And so if we want to calculate the new period via some transformation, we take whatever the coefficient of x is, put it in absolute value, that is ignore the sign, and then 2 pi divided by that b value will give us the new period. Now remember that if we have a negative b, this is going to be a reflection across the y-axis, or a horizontal reflection. Then if d occurs, that is, we take our entire function, we add or subtract a d value, then adding a value makes the whole function move up, subtracting a value makes the whole function shift down by whatever that amount is. Now, phase shift, this is a little more difficult to deal with, and we're just going to state it for now. The phase shift, or the horizontal shift, is the c value. But what's going to happen is that if this entire statement is minus c, it actually shifts right. If the whole statement is plus c, then the whole thing shifts left. So my notation is to match up the fact that horizontal stuff's actually kind of opposite, and so x minus c is the way we've stated it, so be a little bit careful, it works backwards. So now let's actually look at some of these transformations. So, we have y equals negative 2 sine of pi times x. Now what we want to do is we want to graph this thing. But we're going to graph it using this idea of transformations and see if I can get it sketched out. I'm going to use a few other tools since I'm graphing by hand, and if you're graphing by hand, this idea that we're going to use is very helpful. But if you're graphing in MyLabs, and we'll look at this, you just have to pick out the correct information and then do the correct transformations via a slider. So, first off, what's our parent function? Well, our parent function is y equals sine of x. That is what we would get before transformation. Now I'm going to sketch the sine function to try to keep myself on track to remember what it looks like. Okay, this is what that function looks like. Remember that it does keep going forever in both directions, matching that up. Now, and of course, the unchanged has a period of 2 pi and an amplitude of 1. Alright, so if I'm just doing a quick sketch of what in the world does the sine function look like, there it is. That's my quick sketch. But now there's transformations that occur. So notice that the things that are different from the parent function are this negative 2 and this pi. So specifically there's going to be 2 or 3 transformations depending upon the way you look at it. So first off, the fact that we have a negative 2, that's really, in terms of that previous statement, the negative a, that's going to be what? Well, what that does is two things. First off, that's going to be a horizontal reflection or reflection across the x-axis. And so specifically, if I think about that in terms of the graph, what's that going to do? Well, that turns it upside down, and so now the function is going to look like this. So that's what that reflection does. Now, it also does something else, that is, it changes the amplitude. Specifically, the amplitude is now positive 2 because you ignore the sine. Alright? That means that our peaks are going to be at 2, our troughs are going to be at negative 2, as long as we don't have a vertical shift, but we don't. Then lastly, this pi that occurs here is a period adjustment, and so there's a period adjustment. But remember that our period can be defined as 2 pi divided by the absolute value of b, or specifically, in this instance, our b is pi, and so it's 2 pi divided by the absolute value of pi, which is pi. And so this is kind of strange because that means that my period is actually going to be 2. And so, amplitude change, period change, reflection. Now, because I'm plotting this by hand, I'm going to play a trick to find the best points to get. And when I'm thinking about points, I'm thinking about the high points that will come out of the graph. So remember that you have peaks, you have troughs, and you have x-intercepts. So I remember that for sine, cosine, these peaks and troughs occur at nice little intervals. Mainly, some nice stuff happens at 0, some nice stuff happens at pi halves, at pi, at 3 pi halves, and at 2 pi. Then I want to consider that these peaks, troughs, and x-intercepts that I've just kind of labeled in terms of the x of the original sine function, we'll notice that there's 1, 2, 3, 4, 5 pieces that are going to be useful. And so I think that we can use that information and the period that's given to get a complete picture or one complete cycle in the way I need it. And so first off, what are we going to do? Well, what I say to do is take 0 times your period, 1/4 times your period, 1/2 times your period, 3/4 times your period, and then your full period. And those 5 points that we get should give us nice images as long as there's no phase shift. And so let's find the points that I want to use if you want to plug in values. So, of course, 0 times p is 2 here. 0 times p is 0. 1/4 of p, that's going to be a half. Half of p, half of 2 is 1. 3/4 of p is going to be 1.5 or 3 halves. And then my full period is 2. So I claim that if you're trying to pick values for x to plug in this function, these are the x values that you would want to pick. 0 times your period, 1/4 times your period, 1/2 times your period, 3/4 times your period, and your whole period. And if you take those values and you plug them in, if there's no phase shift, you'll get one complete cycle using peaks, troughs, and x-intercepts. And so, then, if I were to plug these values in, specifically into -2 sine of pi times x, I could get ordered pairs to plot very nicely. Well, let's plug in 0. 0 times pi is 0. Sine of 0 is 0. And let's plug in a half. So now we're evaluating -2 sine of pi times a half. Well, sine of pi halves is 1. 1 times -2 is -2. Then let's plug in 1. -2 times sine of pi times 1. That's sine of pi. Sine of pi is 0. 0 times -2 is 0. Then let's plug in 3 halves. So -2 times sine of pi times 3 halves. That's sine of 3 pi halves. Sine of 3 pi halves is -1. -1 times -2 is +2. And then let's plug in that last value, which is the period. So -2 times sine of pi times 2 is equal to, well, sine of 2 pi is 0. 0 times -2 is 0. Now, to help get us on track, where does 2 live? 2 would be about right here, using this current grid. And so, this grid that I've given is really nice when we're dealing with periods that have pi's involved. But just so we can see some comparison, 2 ends up being about right there. And then 1 ends up being about right here. And that means that a half is about right here. And here we have about 3 halves. So in that ballpark, there we are. Well, then I've got to add some other markers. So why did I call this 1, -1, 2, -2? Then when I graph this, well, notice that when I plugged in 0, I got the ordered pair 0, 0. And so I have a point here. Then at the point 1/2, I got -2. Then at the point 1, I got 0. Then at the point 3/2, I hit a peak again, and that's at +2. Then at 2, I got 0. So I claim that one section of this will look like this. And so that is what our graph looks like. Now, for the sake of comparison, the original unchanged sine function would have looked like this. And so notice what happened. Well, if this is sine of x, the red one, well, what happened? The period shrunk. That is, a full repetition occurred much quicker. Then what else did we see? The amplitude changed, so it got taller. And it got turned upside down. So the first thing that happens when we move from 0 was not a peak for sine, but rather a trough. And so for a computer-generated image, to see this a little bit nicer, here we are. So let's do it again. So here, we're now given cosine of 2x minus 3. We're going to do the exact same thing. We're going to talk about the parent function, then deal with the transformations. So, the parent function is what? Well, of course, that's cosine of x. And if we needed to sketch cosine of x to try to keep us on track, cosine of x has a peak on the y-axis. And so, unaltered, this is what one small section of cosine will look like. Then our transformations occur as twofold. Okay, we got 2 transformations here. We have the 2 coefficient, which specifically is a period transformation, right? So remember that our period can be found by taking 2 pi divided by b in absolute value, which means that we have 2 pi divided by 2. That means that our period is actually going to occur in pi. Now, think about this. What's going to happen? Instead of everything occurring in 2 pi radians, we're going to get a full cycle of cosine in pi radians for this transformation. One more thing that happens is that we get a vertical adjustment, and that vertical adjustment makes it go down 3. And so, because of that minus 3 on the outside of the function, we know we're shifting down 3. And so, you're shrinking it and shifting it down. That's all. Now, with that being in my mind, I think I could graph this really easily. So once again, picking key points for x, if you just want to plug in values and get something to line up, you can take and you can multiply 0 times your period, 1/4 times your period, 1/2 times the period, 3/4 times the period, and the full period. Those are the x values that we would want to plug in for x into this transformed function if you're just trying to get ordered pairs to graph. And so, 0 times the period is pi, so that's going to be 0. 1/4 of the period, that's going to be pi divided by 4, or pi fourths. 1/2 of the period, that's going to be pi halves. 3/4 of the period, that's going to be 3 pi fourths. And then the full period is pi. And so then if you were to plug these things into cosine of 2x minus 3, you'll get some values. And so let's figure out what those are. Cosine of 2 times 0 is cosine of 0. Cosine of 0 is 1. 1 minus 3. Cosine of 2 times 0 minus 3. Well, 2 times 0 is 0. cosine of 0 is 1. So 1 minus 3 gives us negative 2. Then cosine of 2 pi fourths, which is really cosine of pi halves, minus 3. Well, cosine of pi halves is 0. 0 minus 3 is minus 3. Cosine of 2 pi halves, well, that's cosine of pi. Cosine of pi is negative 1. Negative 1 minus 3 is negative 4. Cosine of 2 times 3 pi fourths, that ends up being cosine of 3 pi halves, and cosine of 3 pi halves is 0. 0 minus 3 is minus 3. Then cosine of 2 pi, cosine of 2 pi is 1. 1 minus 3 is minus 2. Now, to give us some frame of reference, I'm going to make each one of these tick marks worth 1. And then, when I graph this thing, well, at 0, we have negative 2. At pi fourths, we have negative 3. At pi halves, we have negative 4. At 3 pi fourths, we have negative 3. And at pi, we have negative 2. And so to sketch this, what does this look like? This looks about like this. It's a little bit off, but that's pretty close. And then that's one full cycle. Now, for the sake of comparison, let's actually sketch what cosine would look like on this same scale. Unchanged cosine would have looked like that. But let's confirm what we've changed. Well, notice the amplitude did not change. It was a distance of 1. So the amplitude was unchanged. But the period did change. And so we get this transformed period here, whereas the period for the unchanged function would have been 2 pi. Here our period is pi. And then all we did was shift everything down by 3 points. And so that's how that looks. There it is for comparison in a nicer picture. Alright, now earlier I mentioned to you that sine and cosine look an awful lot alike. So here they are, both laid on the same graph together. The blue one is cosine. The green one is the sine function. I've labeled them, so just trace them if you need to. But what happens? Well, I actually claim that these two functions are truly the same function with what's called a phase shift. Since they appear to be the same, I claim, well, what could happen? What could we do? Well, you could take this point and then all the other key points on the cosine function and shift all of those points over a distance of pi halves. And if you shifted it a distance of pi halves, I claim that they would line up perfectly. If you shift the cosine function to the right by pi halves, that's what that says, is also called phase shift sometimes. Alright, so for a handful more of examples, let's say we want to find the range for the following functions. Now, range being, remember, the y value minimum and the y value maximum that shows out and everything in between for sine and cosine. That's really what we have to deal with. Now there's a way to do this via the amplitude as long as there's a vertical shift. And so, well, the range of my f of x function, because this is unchanged, we already know this one, this is actually going to be from -1 up to +1 inclusive. Alright, but then let's look at g of x. Well, what happened? Well, this is an amplitude change. Specifically, the amplitude here is 2. And so the easiest way to do this, because there's no vertical shift, I claim that we can just multiply our range values via whatever a value is given, and that would actually fix our range for us if you're just trying to answer these questions quickly. Notice that, for the record, this is my f of x, this is g of x, and this is the h of x that's given. And so, what's the range of g of x? Well, because the amplitude changed from 1 to 2, my new range is just going to from -2 up to +2. And we can see that from the picture. Peak is at 2, trough is at -2. Then, let's look here. Amplitude is 2. Once again, no vertical shift, and therefore the range of my h function is going to be from -1/2 up to +1/2. Now, if you have vertical shifts that doesn't work this easily, you'll have to think about it a little more. Well, then, of course, let's find the period. Well, what's the period of f of x? Well, that's unchanged, right? The coefficient here is 1, so really it's 2 pi divided by the absolute value of b, which is 1, which is 2 pi. So then, coefficient of x here is 3. So let's find the period of g of x. The period of g of x is then going to be 2 pi divided by 3 in absolute value, but that's just 2 pi thirds. And then for h of x here, they gave this b value to be a fourth, and so that is the period of h of x is 2 pi divided by a fourth in absolute value, or specifically 2 pi times 4/1, or 8 pi. Then notice graphically how that changes things. Well, 2 pi is our base period. Notice that 2 pi being here, this is my f of x. Then, which function is actually g of x? Well, g of x has a shorter period. That means a full cycle occurs faster. And so this is g of x. And then for that last one, h of x, the period got longer, so one full cycle won't occur until you hit 8 pi. And so that's our h of x. Now let's determine the amplitude and the period of the following. If y is equal to -4 cosine of 3 of x, we know that our amplitude is just the absolute value of the coefficient of the trig function. So the absolute value of -4 is +4, and so my amplitude is 4. Then for my period adjustment is 3, so 2 pi divided by the absolute value of 3 is 2 pi thirds. Then for this one, my amplitude is the absolute value of a half, or 1/2. My period is 2 pi divided by b in absolute value, so absolute value of -pi, which means that my period is 2. So now let's go in the reverse direction. We want to find an equation for the graph shown. And I claim that there's actually 2 ways to do it, but we're going to go for the easiest. Because remember that the truth is that any time you have a sine function, well, you could adjust it and make it a cosine function, or vice versa. They really end up being the same, just shifted left or right. And so I'm going to pick the one that is the most obvious when I have to find an equation. Now, how am I going to choose that? I'm specifically going to look at the y-axis. And I'm going to look at the y-axis and I'm going to ask myself, do I have a midline point, or what I would think of as the x-intercepts, or do I have a peak or a trough? Notice that on the y-axis here, I have a trough. So because I have a trough, or a peak, I'm thinking that cosine is the one that I want to use. So I'm actually going to use the cosine function. Well, then that I know the cosine function, really all that I have left to do is check for vertical and horizontal shift. Because I picked the cosine function, which has a peak or a trough on the y-axis, I'm going to ignore horizontal shift. But I do see that it's actually going to be a vertical reflection. Now, if nothing else, sketch yourself the original cosine function for reference. The original cosine function would look like this, where specifically, this is a distance of 2 pi, and for the amplitude, this is a distance of 1. So that's the cosine function unchanged. Alright, well, how did I get from the cosine function unchanged to this one? A handful of things. I see that there's a vertical reflection. Well, how do I do that? Well, that means a vertical reflection, which means that I need to have a negative a value. Great. I also see an amplitude adjustment. But specifically, my amplitude here is the distance between the peak and the midline, or the trough and the midline. Max minus min divided by 2. But notice that for both of these, I get that the amplitude is 3. And so I know now that my amplitude is 3. So I know that I'm going to have a negative 3 as the coefficient of cosine. Alright? We're heading in the right direction. Negative 3 cosine of some stuff. Alright. Notice that my midline here is at 0. And so since it's at the x-axis, there's no vertical shift. So luckily enough, I get to ignore that. Then, all that I've got to worry about is my period. So let's label a full period. So, measure from peak to peak. So peak, peak, that's peak to peak, that's 1 period. Well, what's the distance? The distance is going to be the maximum minus the minimum, or 4 minus 4, which is 8. So I know now that my period is 8. But remember that my formula said that my periods were equal to 2 pi divided by the absolute value of b. Well, my period being 8, so 8 is equal to 2 pi divided by absolute value of b, but since we're not having a horizontal shift, you can really ignore the absolute values here. Then we just need to solve for b. Multiply both sides by b, then divide by 8. That gives me that b is equal to 2 pi divided by 8, which simplifies to pi fourths. So now I have that b is pi fourths, and so cosine of pi fourths of x times x is the function that I want. And so f of x, or y, is equal to this. This takes care of my vertical reflection, reflecting across the x-axis. My amplitude adjustment, which made it taller, and the amplitude is 3. And then my period adjustment, which gave my period to be 8, but the way we do that is with a value of b being pi fourths. Now, because you're going to have to work in MyLabs, let's actually graph some of those in MyLabs Plus so you can see what they look like. So now let's look at this MyLabs problem and walk through the interface with MyLabs. So let's just find this information that we need to find first. So we're given that 240 times sine of 40 pi t is the function or the equation that we're concerned with. So let's first find the period. Remember that our period is 2 pi divided by the absolute value of b. And so b here is actually what? It's 40 pi. So 2 pi divided by 40 pi. That gives me 1/20th. So then we get that the period is 1/20th. Next question is, what's our amplitude? Well, remember that amplitude is going to be the coefficient of sine or cosine, and so our amplitude is going to be the absolute value of 240 here, or 240. Then we need to graph. And so how are we going to graph this? Well, step one, notice that there's a cosine tool and a sine tool in this problem, so pick the sine tool because that's the sine. Then just pick a value. Anywhere, just touch the screen, it gives it to us. At this point, now we just need to answer the questions that are asked. So, what is our amplitude? Well, we found our amplitude to be 240. Then, what is our period? Well, we found our period to be 1/20th. Then, do we have any vertical shift? Notice that there is no vertical shift. There is no addition or subtraction to the entire sine function. Then we want to know, is there any phase shift? Phase shift would be any changes left or right, but that would be additions or subtractions inside the function, but there's no addition or subtraction here, so there's no phase shift. Then vertical reflections, or reflections across the x-axis, that would show up as a negative in front of the amplitude change, but there's nothing there, and so there's no reflections inside, or no negatives inside the function, so there's no reflections over the y-axis either. And so, we're done. That is our function, and we have graphed it. Now let's try our hand at graphing a cosine function. So, we're given that y is equal to 5.35 times cosine of 2 pi divided by 365 times x minus 2 plus 12 plus 12.45. Now before we start talking about the transformations that occur to this specific cosine function, we need to make sure it's in the correct format. And when I say the correct format, we need to actually factor b out of this binomial so that we get the correct phase shift. And so this is going to be 5.35 times cosine, factor out 2 pi divided by 365, but 2 pi divided by 365 divided by itself is 1, so that's going to leave us with 1 times x, minus, well now I've got to factor 2 pi divided by 365 out of negative 2, so 2 divided by 2 pi over 365. Fraction division is fraction multiplication, that's going to be 2 times 365 divided by 2 pi, and so 2 divided by 2 is 1, that's going to leave us with 365 divided by pi. 365 over pi, all added to 12.45. So now let's address everything that just happened. Now I can talk about all my transformations. So, specifically, that's my amplitude. This is b, which of course relates to the period. This phase shift, specifically it's going to go right 365 over pi, and then this is a vertical shift. Specifically it's going to go up 12.45. So that's every bit that I need, almost. I do need to calculate the period, so let's calculate the period real quick. The period is equal to 2 pi divided by b in absolute value, which means that this is 2 pi divided by 2 pi times 365. Absolute value of positive is positive, so then fraction division is fraction multiplication. Multiplication by the reciprocal, copy dot flip. 365 divided by 2 pi. 2 pi divided by 2 pi is 1, and our period is going to be 365. Alright, then notice that there was no negatives for A or B, so there's no reflections. So then, let's graph it. So, this was a cosine function. Notice that one of these is a sine function, that's the sine tool. This one is a cosine tool. So, this is cosine, I'm going to choose cosine. Then just tap on the graph. Then we need to type in our new amplitude. Well, what is our new amplitude? Our new amplitude is 5.35. Then we need to type in our new period. Well, what is our new period? Remember, we just calculated our new period is 365. Then I need to plug in my vertical shift. Well, it goes up 12.45, so it's going to be positive 12.45. Then I need to type in my horizontal shift, and my horizontal shift is to the right, or positive 365 divided by pi. Now, notice that I did have a minus here, but remember that phase shift is actually backwards. So if I have minus, it's going to be a positive shift. So it's a horizontal shift of 365 divided by pi. We're done. Then we check it. And there we are.